Hello and welcome to Toddcast number 38. So we're continuing with elimination, but this time, instead of looking at E1 versus E2 in terms of city conditions, basic conditions, we're going to focus on something called Zaitsev elimination, where you get the more stable, the more favorable double bond, but also the Hofmann elimination, where you end up getting the less substituted double bond. They're both eliminated or elimination reactions, but you can alter the conditions of the reaction to favor one over the other. And that's what we will focus on in this one. So what we'll end up doing is we'll use the exact same reagents and see what happens to an alkyl halide. So when you have beta H's that lead to different products, then here's what we're going to have. So what we mean by this, here's my alpha, my carbon the leaving group, one carbon over, there's an H, but one carbon over here, there's three H's. So those can also be eliminated. So I'm going to get rid of my writing and let the computer writing come in. So there's my alpha, as mentioned, and here's my beta, and I'm going to call this beta prime. So the difference between the beta and the beta prime. Beta is going to lead to the more substituted double bond, more stable double bond, but it's really crowded to get there. There's two R groups that you have to work around to get to that H. These are easy to get to, but you get a less stable double bond. So the question comes down to, would you rather get a more stable double bond, or would you rather get to the H's more easily? And you're always going to have a competition between the two. So we have used ETONA. That's just two carbons. That's not all that large. So this isn't that restrictively bulky. And two R groups, although bulky, not restrictively bulky like three would be. So it's going to be able to come into this one fairly easily and get this product. This one can also go here and it'll end up doing both. So the so-called Zaitsev product, I'm going to put a Z. I'm actually going to spell it so it doesn't get mistaken for Z alignment like E and Z. And this is going to be Hofmann. And you're going to hear me say hefty Hofmann. I'm going to say it a lot because the way that we end up making this one more favorable is by making the base so bulky, so hefty, that it can't come in and get this H, it doesn't fit, so it's forced. So hefty Hoffy, when it's a hefty base, it goes Hofmann elimination, hefty Hoffy. Zaitsev, more stable, hefty Hoffy. When you have a bulky base, you have a tendency to get more of the Hofmann. So less stable because it's only got one R group on it, more stable because it has three. So tri-substituted beats mono-substituted, but easier to get to. So kinetically more favorable. And sterically, it's hard to get to this one, but you end up with more stable products. So thermodynamically more favorable. So this is my thermodynamically preferred product. This is my kinetically preferred product. So the Zaitsev product, the thermo product, and the Hofmann product, the kinetic product. So if we were to use the same compound, this has been well studied, we're going to look at the percentage of which one we get. So the percentage of the Zaitsev product, percentage of the Hofmann product, the base we chose, and the temperature we chose. So for this particular reaction, we use ETONA at room temperature around 25 degrees. When we do this, we end up getting about 67% of the Zaitsev, about 33% of the Hofmann. Okay, so the way we're going to control selectivity, the choosing of this beta over this beta, is by either A, changing the size of the base, or B, changing the temperature. So if I use a base that gets smaller and smaller, then I expect this percentage to get even higher, this one to go down. If we use a base that is bigger, then this one becomes a little more restricted for the base to get in there. So I start seeing more and more of this product. So if I were to use something like T-butoxide, potassium T-butoxide, very, very bulky base done at room temperature, ends up I now get 70% of Hofmann, 30% of Zaitsev. So the shift in the base size forces it as the base gets larger to go to the less crowded side. So it chooses the so-called kinetic or easily accessible H's as opposed to the more stable H that leads to the more stable compound. We can also mess with temperature. So we're going to use this same base, but going to use higher temperature. With higher temperature, you can overcome, like you can force the base to come into this side. And in doing so, a little more of this product, a little bit less of this product. So as temperature goes up, reactions become less and less selective, and you start getting closer to 50-50 mixtures, generally speaking. Bulkier bases favor the Hofmann, smaller bases favor the Zaitsev. It would rather be Zaitsev, but if the base is too large, it goes for Hofmann. Hang on to this thought because if you understand this, you will understand a lot of chemistry and biochemistry that'll come your way over the years. So as a base and or the leaving group gets bulkier, so we're doing an example, we're showing a bulkier base. We can also do a bulkier R group on the structure itself. So whether the leaving group is adjacent to something much bigger, or if base is bigger, as long as you have two large molecules, then you start getting more and more of the Hofmann. Okay, so traditional Hofmann elimination. As it was proposed, uh, he had a unique approach, and that was he took an amine, and this is a primary amine, so N on just didn't do pentane. That seems to be the one I'm addicted to doing, but it could be any chain length. But chose here, rather than putting it on the N, we put it on the second carbon, and we're going to have excessive amount. So excess, QC way to say excess, lots and lots of CH3I. Ammonia, if you recall, is a very good nucleophile. Going to attack, kick out the I. You cannot get elimination with the CH3, which is why we choose it. So there are no beta hydrogens. So this is the alpha carbon. So these are all alpha hydrogens. Can't get elimination here, but you can get elimination here. That's what our goal is. So Hofmann took a small group, methylated it, and made a big group. So just like we used, if you think about the base we just used, the base we used was these same three here, H3C, H3C, CH3 connected to an O minus. That was a bulky base. This is now a bulky leaving group. We're doing the exact same thing, but instead of making it a bulky base, we're now going to use bulk on the leaving group. Okay, so we go ahead and we add these three, gives it a plus charge, so it's a great leaving group. So now that I have this, I have beta here and beta here, but again, this is alpha, alpha, alpha. There are no beta, so you cannot get elimination, so elimination can only happen here. We use, in this case, a metal oxide, sodium hydroxide, potassium hydroxide, those would work, but silver works exceptionally well because it binds and forms a solid with AgI, which prevents any back reaction with iodine and ends up with a very clean reaction, and the amine comes off quite easily. So when it leaves, it's going to be N with three CH3s and no more charge. Okay, so if we look at the two H's, so let's consider the left here and then the right one here. Let me actually do it on this side. So this is the right one. This is the left one. So here it's a CH3 connected to the carbon with a bulky group. So here's my C with three H's connected to the bulky group and the rest of the chain. On this side over here, we have this one with an ethyl coming off the front. So this group here, an H, another H, and then the group going back, the alpha carbon with a methyl, and the big bulky group. So I have to have anti-alignment. It ends up, any of these H's can be anti-aligned. This group right here is anti this H, but if it rotated around, it'll be fine. So you have the leaving group and the H anti. On the other side, you have the H and the leaving group also anti, but, and this is the big but, it ends up that this group is gauche to this group. This bulky group, which these can rotate around and interact in the middle of the molecule, and this group, which can interact. So if you recall from your Newmans, you do not want bulky groups near each other. So this group right here, the CH2, I'm going to draw it like this, emphasize that it can get in the way and back. And then the nitrogen group of the CH3, CH3, and a CH3, which gets in the way right there. So you start running into steric hindrance right there. So these groups do not want to be gauche. You rather rotate it around. So let me get rid of this drawing and say then that it ends up, this is how it would rather line. So this is no longer anti. This H and that H are not in the right alignment. So it takes too much energy to rotate this up into an unstable gauche conformation to get the elimination. So it ends up, it's just going to take the easiest route it can, and that is to take the H on the left side that can be easily anti. This one cannot be easily anti. So ends up, we only get this, or not only, but we get predominantly the Hofmann. So we take advantage of either a bulky base or a bulky leaving group. Okay, so the Hofmann elimination, why is it necessary? Well, you want an E2, not an E1. So E1 would be with rearrangement, so I can get rid of those choices. So it's E2 because we're using a base under basic conditions, but you don't really want rearrangement. You just want it, you don't, I mean, that's not going to happen with E2 anyway. You're trying to do it because you want a non-Zaitsev alkene. You want the Hofmann product. The Hofmann, you want the one that's less substituted. So Hofmann versus Zaitsev is a question of what they call regioselectivity. It chooses the less substituted region of the molecule to form the double bond. Okay, so hopefully that makes some semblance of sense. So here's how we're going to decide what the E2 is. Okay, so first and foremost, always identify what the alpha and beta carbons are. Alpha is the easy one that has a leaving group. Beta is the next carbon over, and consider the H's on there. If they are non-equivalent, that means if you have, let's say, a methyl and an ethyl group on the alpha carbon, then the methyl is smaller than the ethyl, so they are not equivalent. So therefore, you have to consider the size of the base. If it's a bulky base, really large base, then it's going to choose the less hindered beta H. And if it's a small base, it'll choose the more stable, i.e. the more hindered H. So small base will go to Zaitsev product, bulky base, Hofmann product. So hefty Hoffy, bulky base, a hefty base will go to a Hofmann product. And then you have to align and rotate the molecule because it's an E2 elimination reaction. You have to align it so that the H and whatever leaving group, Br that I'm using in this case, are anti to one another, and then just get rid of those two, rotate the orbitals into place, and make your pi bond. So for instance, T-butoxide, that's a really bulky one, bulky base, so it's going to choose the less hindered. So alpha is right here. So I identify the alpha, the betas can be here, here, and here. It ends up, these are equal, they're both CH3s coming off the alpha. And then this is your bulkier one, this is your secondary, these are your primaries. So if you're using a bulky base, then my thought process is hefty, therefore Hoffy. Hofmann elimination. So hefty Hoffy. So if it ends up going Hofmann elimination, that means you're going to go for the less substituted H's. So your double bond is going to be on terminals, carbons. Okay, so bulky base, hefty Hoffy. And just to verify it, achiral, nil chiral center. In the end, you still have no chirality. Not that if you went here, you'd have any chirality as well. But sometimes it's good to monitor that. These side products are butanol, T-butanol, and then this say K is the leaving group. So the K here is going to bind with the mesylate group. So far, so good. If you use NaOH, much smaller, now you can get that double bond. So here's my alpha, and here are my betas. My small one was preferred with the bulky base, but with the small base, I'm going to prefer the more substituted double bond. Again, the chirality doesn't seem to matter here. Bringing it up because I want to get in a good habit of paying attention to all the details. Okay, so this time OH combined with the H to form water instead of T-butanol in the same group coming off. Hofmann product, Zaitsev product for the lower one. Okay, so let's look at another example. So in this case, OTOS is my leading group. So just like um, with OH to make the leading group for SN1 or 2 reactions we talked about, same thing is true for elimination. If I have an OH, I can turn it into an OTOS, an OMES like the previous examples, or OH and protonate it. So if I use a bulky base, if I protonated and made it water, then it would just deprotonate it, and that would undermine the whole process. So I'm going to convert the OH into an OTOS or an OMES. When I do this, this base here, again, is kind of that intermediate size. So as we saw in that table reaction, when we used a base this size, you kind of got a mixed bag. You got a little bit of both. So you have my alpha, the beta, and beta. So size, it still would want to, small enough that it still can get in here, but this is a trick question. There is no H here. There is a CH3, a CH3, and a CH3 connected to a carbon with one of the carbons. So it's 4 bonds for carbon, 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 and carbon. There is no H. So no H's. It has to be that. So medium base would have been a mixed bag. So in this case, you start out with a chiral compound, in it with a chiral. So now you can actually monitor the reaction by the elimination of the chiral center. Okay. It could have also gone to well, it couldn't have gone that side. So never mind. For this one, now I'm going to have a case where I can worry about my chirality. So this is chiral, 2 chiral centers, small base. So it's going to have a propensity to choose the less or the more stable, the one that's going to size-wise doesn't really matter. There is no less hindered, more hindered. For something as small as OH, going to choose the more favorable. So small base has a tendency to go for small sides. So it's going to go where small base will fit in. So it's going to go for that H. If the CH3 is in front, then the H must be in back, which means they are aligned correctly. This is down and in front, up and in back, they are anti to one another. So you're going to get your product. Same reaction, but a different diastereomer. So this center stays the same, but the CH3 is now in back. So one of the 2 chiral centers change. So these are diastereomers. So this diastereomer leads to what we'll refer to as this group and this group being opposite one another. So they're E. Here, the H that comes in, there's my alpha, there are my betas. Again, small base, so it's going to choose this one. Small base, achiral, but the H is now in front. And so the problem I run into in this case is it's aligned the wrong way. So I'm going to have to rotate everything to get that H back in that position. So the molecule is going to have to turn into, I'm going to run in, I do apologize. I'm going to have to write it really small and in the way where my product's going to be. BR is going to be there. I'm going to leave the BR in the same spot. And then over here, I have to rotate the H there, which means the CH3 is going to be here. And the ethyl group, this group right here, has rotated up into the H spot. So now when these get eliminated, the CH3s are opposite one another instead of on the same side. So syn alignment, you have to rotate it. The reactant must be rotated, and it just so happens I wrote right in the way of it, and I apologize for that. And it's also just really hard to see. It's just, unfortunately, when I get to the bottom of the page, it doesn't turn out very well. But the key point is the ethyl is going to be on opposite sides. So in this case, the bulkier groups on the same side, so same side cis. So that is a Z product. So different diastereomers will lead to different geometrical isomers, and you still end up having um, the chirality influencing it. So it's optically inactive, but they are still stereoisomers. You have an E as opposed to a Z. So key things, lots going on here. Hofmann versus Zaitsev. Small bases goes for Zaitsev, the more substituted. Hofmann will go for the less. This one wasn't really a case of that. It was no H's here anyway, so there was only one H to pull from. So this is more of a trick question. Lots and lots of information. This is a topic that only comes from doing tons and tons of practice questions. So on that note, thank you for joining in, and I am going to tap out, and I will see you at the next podcast. Until then, bye.